Okay, so this presentation is about polar codes, which are capacity achieving codes. Polar codes can be used both for source coding and channel coding, but our presentation is limited to the discussion of polar codes being used as channel codes only. Uh, so before presentation formally starting it, let me introduce myself. My name is Tufail Ahmad. Previously, I was an MS student in Belkent University. I was a research student of Professor Erdal Arikan, who is the inventor of the polar codes. In this presentation, I will try to discuss polar codes, their encoding and decoding, and also give you an idea how or why are they capacity achieving codes. So let's start formally with the presentation. So to motivate some interest in polar codes, in fact, why are polar codes so important that one should know about polar codes? I have listed down some of its very important features. In fact, people of different fields can be interested in polar codes. Information theory and coding theory knows that Shannon suggested long ago that there must exist some codes. He suggested it using his random coding approach, that some capacity achieving codes exist, but nobody was able to explicitly construct such codes with low encoding and decoding complexity. Polar codes are first such codes which can be shown to achieve the capacity of a channel and also have a very efficient and explicit construction, and their decoding and encoding complexity is very manageable of the order of n log n. For hardware guys, just recently Arikan himself uh, proposed an ASIC implementation of a 1 terabits per second throughput polar decoder. Uh, and for optical communication guys, they are working in low bit error rate regions when SNR is high. So polar codes do not suffer from error flows in these regions like LDPC and turbo codes, which suffer from error flows when we have to apply some post-processing algorithms techniques to cater that problem. Last but not the least, the feature which the students of polar code appreciate the most about polar code is that when one studies polar code, they develop a new perspective of the channel coding problem. And due to this new perspective, which Arikan introduced using his polar codes actually, you start thinking differently about the channel coding problem. Due to this, polar codes, their learning has become very easy actually, and in fact, very interesting it is to learn. So conventionally speaking, channel coding means to uh, process a bulk of data, you can say a chunk of data, and add some intelligent redundancy into it. Uh, so Arikan, this new perspective of channel coding, uh, rather than processing the data, and why not we process the channels? We transform the set of ordinary channels into new extreme channels. By extreme channels, I mean perfect channels or useless channel. So that we obtain a new set of channels which are extreme, so that no coding is required on these new channels at all. So this is a new perspective, and this process of transformation of ordinary channels into new extreme channels is called channel polarization. So polar code is about channel polarization. So if we understand channel polarization, we will be able to understand polar code. I will try to explain channel polarization. Channel polarization is a two-step process, combining and splitting. Both processes are lossless. By lossless, I mean the capacity is conserved in both the process. So we take n identical copies of a channel W. They are independent channels. We combine them in a way so that no capacity is lost, and we make a vector channel, or you can say a combined channel. Then we split this vector channel or combined channel in such a way that we again end up in n channels. But these new channels, new in n channels, are not alike anymore. They are not identical anymore like the original channels from where we started. These new channels are polarized in the sense that they are polarized in capacities. So some of the new channels get more portion of the capacity. They nearly became perfect, and some of the new channels become nearly useless, so no data can be transmitted over them. So we started with n identical channels, and applying the process of channel polarization, we ended up in new n channels which are polarized. We call them extreme channels or extremal channels. And when we get extremal channels, so no coding is required on them. If it is a perfect channel, then it is without any noise, so nobody requires coding over it. Just transmit the data as it is. And if it is a useless channel, so it is pure noise, so you can do nothing about it. No matter what type of strong coding you apply, you cannot transmit data over it. So just fix it to some value which is known both to encoder and to decoder. So channel polarization converts such ordinary channels like mediocre channels whose capacities is in between perfect channels and useless channel. We convert such ordinary channels into extreme channels. To explain channel polarization, let us first understand our channel model. We will be considering our discrete memoryless channel W, whose input is X, which is distributed over 0 and 1. So we have binary input discrete memoryless channel. Its output is Y, which will be discrete. It can be continuous as well, but due to our notational reasons in this presentation, we will be considering probabilities rather than densities. We will limit our discussion to those channels whose output alphabet is discrete. But this does not mean that the application of polar code is limited to those channels only whose output is discrete. Polar codes can be applied to those channels also whose output is continuous, but they need to be binary input channel and memoryless and symmetric channels. So another term is mutual information. When we see such term, this is a very common term in information theory, but we will sometimes steer over this term too much. We will use it a lot in this presentation. So when we see such term, we need to know that there is a channel, underlying channel, whose input is X and output is Y, and this term I of XY represents its mutual information. So further, among binary discrete memoryless channel, we will be considering symmetric channels only. Why only symmetric channels? I will explain this in next slide. But a binary symmetric channel is one which has input and output symmetry. The famous examples are binary symmetric channel with erasure, binary symmetric probability epsilon, and binary erasure channel. These two are having discrete inputs and discrete outputs. Similarly, binary input AWGN channel is also a binary symmetric channel whose output is continuous. So polar codes are applicable to these channels as well. Okay, so now we can answer why are we considering only symmetric channels. Polar codes are linear codes, and linear codes in general cannot achieve the capacity of any arbitrary channel unless and until the optimal distribution, or you can say the capacity achieving distribution on the input alphabet, is uniform one. And symmetric channels are such that the capacity can be achieved if the input alphabet is uniformly distributed. For example, say if we have binary alphabet and the input alphabet is uniformly distributed over 0 and 1, then the capacity of the symmetric channel is given like this, I of xy. So, and we will denote it by I of w with the two assumptions that w is symmetric and the input to w is uniformly distributed over 0 1. So whenever we replace a term like this with this, we will have these two assumptions. About polar code, let me tell that the claim about polar code is that they achieve the capacity of symmetric channels, or you can say this in different form, that polar codes achieve the symmetric capacity of any channel. But for symmetric channels, the Shannon capacity, as we know, the Shannon capacity and the symmetric capacity are the same. And for other channels, the Shannon capacity and the symmetric capacity are different. So the gap to capacity, people know that gap must be they can cover that gap using the distribution of the input alphabet. But that is not our problem. That is a different problem at all. So we are considering only the symmetric capacity, which is the same as a capacity for a symmetric channel. So we will be using base 2 logarithms. So at the maximum, the capacity can be equal to 1. At the minimum, capacity can be equal to 0. So a perfect channel has capacity 1 and a useless channel has capacity 0. Mediocre channels or ordinary channels has capacity between 0 and 1. So channel polarization, which spirit is Arikan's polar transform. Its application causes channel polarization. So its Arikan's polar transform converts ordinary channels or mediocre channels into such extreme channels. And this is a two-step process, combining and then splitting. So let's start with the basic polar transform, combining of two channels. And then we will generalize this to many channels. So consider two identical copies of binary symmetric channels. These channels are symmetric and they are independent. So the input alphabet x1 and x2 are independent because each one is achieving the capacity. If you want each one is to achieve the capacity, the input alphabet should be uniformly distributed over 0 and 1. Now, if we want to combine it using polar transform, this is the process of combining. We combine this is using a G2, which is a basic polar transform and works like this. X1 is equal to U1 plus U2 and X2 is equal to U2. In matrix form, it can be written as the first row 1, 0 and the second row written as 1, 1. We call it G2. So this is a one-to-one transform. So the input vector is also of the size 2, output vector is also of the size 2. Okay, so here it is very easy to see that if U1 and U2 are uniformly distributed over 0 and 1, then since this is a one-to-one mapping, we have one-to-one mapping polar transform, and these are uniformly distributed over 0 and 1 and independent. And so we also end in x1 and x2, which are also independent and each uniformly distributed over 0, 1. This is due to the one-to-one mapping and the input alphabet being uniform from the beginning. So we get uniformity over here as well and independence over here as well. So we can write that the capacity term, this one, we can split it into two terms because x1 and x2 are independent. So each channel has capacity IW because we have got x1 and x2 to be uniformly distributed. So we can write these mutual information as the capacity of the channel because the channels are symmetric and the input alphabet is uniformly distributed over 0 and 1. So we have no problem in writing this. Further, we know that we have one-to-one mapping between U1 to U2 and X1, X2. So from one we can determine the other and vice versa. So we can write this equation also. So, and this is also equal to 2IW. So we end up in a combined channel whose input is U1, U2, output is Y1, Y2. So the capacity of this channel is equal to the sum of the capacities of two independent identical channels. So we lost nothing in this combining process. Okay, the next step is that of splitting. So we got a combined channel whose capacity is the same as that of the sum of the capacities of two independent identical channels. Now we can split this term. So if we apply chain rule of mutual information, we get two terms. In fact, we got two terms of mutual information and we have mutual information of two channels. Inside the parentheses, we got a channel whose input is U1, output is Y1, Y2. Another channel input is U2, output is Y1, Y2, conditional to U1. We can further simplify this like this because we know that U1 and U2 are independent of each other, so we can write it like this. So now we have two channels and both the channels, the input are U1, U2, which are uniformly distributed over 0 and 1 and are independent. So these two channels are independent as well. And these two channels input alphabet is a uniform, so they can achieve the capacity. So we write this channel as the capacity of W minus channel and the capacity of W plus channel. We denote these channels by W minus and W plus. Why we call it W minus and W plus, we will make it clear in the discussion to come. So, but the thing is that we started from combining two identical channels and we ended up in two new channels after channel polarization process, and such that these two new channels are not identical anymore in their capacities. So we started with identical channels, we ended up in polarized channels. We will explain why are they polarized. So we got two new channels, W minus and W plus. This is our notation. Okay, so let me explain why these channels are polarized. So we got these two polarized channels. They are their explicit form. So we consider W plus channel here, we see, and consider its capacity. So W plus is a channel whose input is U2 and output is Y1, Y2 and U1. Okay, we see that this channel contains inside another channel whose input is U2 and output is Y2, like this one. But this channel cannot be better than this channel because this channel has an additional information at the observation as Y1 and U1, which can help it in the decoding of U2. So W plus will be clearly better than or equal to in terms of capacity is this channel, and U2 is nothing but X2 itself. As we see, U2 is X2 and the channel amount between X2 and Y2 is W, so this is equal to I of W. So we see that W plus channel can be better than or equal to the original channel. So, and we have the capacity conservation because the sum of the capacities of two polarized channels is equal to sum of the capacities of two independent identical channels. So if W plus is better than the W and this one to hold, then W minus must be worse than the original channel or equal to the original channel. So one is better than the original channel and one is worse than the original channel. So we got two new polarized channels. One is such that whose capacity is more or equal to the original channel, and other one is such that whose capacity is less than or equal to the original channel. The equality holds firmly when we start with a original channel which is perfect or useless. If we start with mediocre channels, then these equality signs will vanish and only greater than and less than signs will hold. So here we get a sense of polarization by combining two channels. This is not a perfect polarization. We did not end up in a perfect channel and useless channel, but we polarize the identical channels in some way that these channels have either become a little bit better or a little bit worse. We will explain it. Let us consider it in more detail. The first channel W minus, input is U1, output is Y1, Y2. Okay, so the U2 is acting as random noise because it is uniformly distributed over 0 and 1. So it corrupts the transmission over U1, as we can see. So this clearly worsens the channel W minus because this is acting as noise. And thanks to Y2, we have a slight estimate, or you can say estimate of U2, due to which we can somehow decode U1 as well. But without U2, this channel would have been totally useless. But due to U2, this U1 can be decoded, but not as efficiently as there were no combining process at all. For example, if we do not have this combining, U1 could have been transmitted over Y1 and there was no noise added, but due to this U2 being added as noise, this worsens the channel W minus. So clearly this is a worse channel. W plus channel, it becomes confusing sometime. Input is U2 and outputs are Y1, Y2 and U1. Sometimes people get confused how output is U1 because U1 is an input to a channel W minus. So they get confused here. But I will try to explain. And let us consider the decoding process. We have Y1 to Y2 available as observations. And let us assume that we know U1 before decoding U2. Somehow we know it correctly. Then we have three observations, U1, Y1 and Y2. So if we know U1, if we know the U1 value, then U2 is clearly transmitted over here as well, and U2 is clearly transmitted over here as well, just like a repetition channel. So the capacity of the W plus, or you can say the quality of W plus, is clearly better than the original channel W. So this is due to the fact that if we know which is a prior bit as compared to U2, if we know it before. So decoding order is very important in polar codes decoding, which gives rise to successive cancellation decoder. This is a famous decoder for polar codes, which can be used to show that they achieve the capacity of symmetric channels. So in a successive cancellation decoder, if we want to decode a given bit, we must know all the bits prior to that bit. We must know them correctly. So this W plus channel, we saw this is better than the original channel W, and we saw W minus channel was worse than the original channel W. So now the question is, can we know all the prior bits to decode a given bit? The answer is yes. Asymptotically speaking, when we apply polar transform many times, we end up in channels which are either perfect or useless. So if we want to decode a given bit, all the prior bits to that bit, all the bits which are decoded before that, they must have been either input to a perfect channel or to a useless channel. If a prior bit was an input to a perfect channel, then we know it can be decoded correctly with probability 1. If it was an input to a useless channel, then we know it can be it was frozen to some fixed value, and we can know it for sure because both encoder and decoder have information about that. Up till now, we consider just general cases. So let us consider an example to make things clear. We consider a binary eraser channel whose input is equal to x, output is equal to y. Output can be equal to input with probability 1 minus epsilon, and output is lost, and we ended up ends and erasers are question mark when the probability with probability epsilon. So consider W minus channel. Its input is U1 and output can have 4 possible cases. So can we decode from these 4 possible cases the U1? So let's explain it. In the first case, we have U2 and U1 plus U2. So clearly we can decode U1 from here. Here we end up in Y1 being lost and U2 is known, but U2 is independent of U1, so we cannot decode U2. Similarly, we have U1 plus U2 but no U2, so we cannot decode U1 again. Clearly, we cannot decode U1 here. So the only case which ends up in being capably decode U1 is this one. So the erasure probability is 1 minus this probability. All the other thing, all these probabilities are the erasure probabilities, erasure cases. So the new channel is a binary erasure channel also with erasure probability epsilon minus, which is equal to 1 minus the first term. So 2 epsilon minus, which is clearly greater than the original epsilon. So we ended up in a channel which is a bad channel. For example, if we started with the original channel being epsilon 0.5, so we ended up in a W minus whose erasure probability is 0.75. So we ended up in a bad channel. Consider W plus, input is U2, output Y1, Y2 and U1. Can we decode U2? So we consider all the 4 possible output cases. In the first 2 terms, we see that U2 is explicitly available, so U2 is decoded. In the next term, we have U1 and U1 plus U2, so we can decode U2. Here we have U1, which is independent of U2, so we cannot decode U2. So this one end erasure, so the erasure probability is epsilon. So we got a W plus channel, which is a binary erasure channel itself, with erasure probability epsilon plus, which is equal to epsilon square, which is clearly less than the epsilon. So if we start with the original channel erasure probability 0.5, then we ended up in a W plus channel whose erasure probability is 0.25, which is less than the 0.5. So we ended up in a good channel. So we combined 2 erasure channels, each with 0.5 erasure probability, and we ended up in 2 polarized channel, W minus and W plus. One has erasure probability 0.75, bad channel, and another end channel with erasure probability 0.25, a good channel. Up till now, we consider only size 2 construction of polar codes. If we want to construct large size polar codes, we have to apply the polar transform repeatedly, or you can say recursively. Let us say if we want to construct size n polar codes. So what we do, we take size n by 2 construction, duplicate it, and then we apply the polar transform to identical channels among the duplicates. I will explain it what is identical channels. Let's say size 2 construction. So we take size 1 construction, which is the original channel W itself. We duplicate it, WW, and both are identical channels. So we apply polar transform to these channels. So we get 2 polarized channels, W minus and W plus. Consider size 4 construction. We take size 2 construction, which we have a W minus and W plus channel. So we duplicate it. Here we see we duplicate size 2 construction. Now we have 2 identical channel W minus and 2 identical channel W plus. So we get 4. If we apply polar transform to the pair of W minus and pair of W plus, we get 4 polarized channels, and so on. We can do it for longer block lengths, larger block lengths. Let us see it in a picture to make it clear. We want to construct size 4 polar codes. So we have size 2 construction. We take it, we duplicate it, and we have two W minus channels now. Here is W minus, here is W minus, here is W plus, here is W plus, like we see it here. Now we apply polar transform to identical channels, to a pair of W minus and pair of W plus. And since we know we decode W minus before W plus, so we have to decode this bit first, then decode this bit first, then this is another minus channel when we combine two W plus channel, so we end up in a W plus minus. Decode this one, and then we at the end decode this one. So decoding order is important. If we decode it in this way, which I have discussed already, U1, U2, U3, U4, which is a bit reversed order, then we end up in four polarized channel like this. So decoding order is important. Only then we can end up in polarized channel. If we do not follow the decoding order, we may end up in bad channels as compared to the original channels. So overall for size 4 construction look like this: size 2 construction, size 2 construction, then applying polar transform to identical channels. We can rewire this. I can take this modulo 2 addition outside towards source and this towards the channel. So this is again the same, but just it will help us that now we can decode in the natural order: U1, U2, U3, U4. So people like this, people using polar codes for encoding and decoding like this order very good, because very much because this is a natural order. Now if we want size 8 construction, we duplicate it and apply polar transform. So this is size 8 construction. Okay, and now to show how polarization is it the case that polarization is really happening? Let us demonstrate it by an example. We consider a binary erasure channel. Epsilon is its erasure probability. We construct size 2, so we end up in two channels whose erasure probabilities are these. So epsilon minus, epsilon plus. So if we again combine 2W minus and 2W plus, so we end up in four polarized channels, and recursively their erasure probabilities are given as these. So this happens recursively, very explicit construction for the erasure probabilities and so on. So we can see now. So we saw size 2 construction was not that much polarized, but polarized in a little bit. So we see when we increase the block length, what happens. We see size 16 block length construction. We combine 16 channels, polarize them. So we end up in some channels which are nearly useless. Their capacity is 0. Okay, the original channel has erasure probability 1/2, so its capacity is 1 minus erasure probability, which is 0.5. So the original channel has capacity over here, but we ended up in 16 channels whose capacities are distributed all over the plot. But some channels are useless, some channels are totally perfect, capacity 1. There are still some channels which are mediocre channels. We don't want them. We want all the channels to either lie here or either lie here, either totally become useless or perfect. So we want these channels, number of these channels to be very low as compared to the extreme channels. So let's increase block length and see what happens. So the number of channels with extreme capacities is increasing as compared to the mediocre channels. If we block length 64, we see it more clear. 128, even more clear. 256. So the number of channels lying over here increases, but they are overlapping, so one now cannot see all these channels as compared to these channels. So let's consider 1024. So the number of channels here and here, their number is more, in fact, with huge difference as compared to these channels. But since these channels are scattered, so one see that one get a false impression that maybe these channels are more as compared to the extreme channel, but this is not the case. So extreme channels are more as compared to the mediocre channels. We will explain it. Okay, now let's consider the general case for a block length n. Polar codes can have block length of n, which is equal to 2 to the power some integer. It cannot have an arbitrary block length. For example, let's say 14. If you want a block length other than 2 to the power some integer, for example 14, let's say we construct a polar code of 2 to the power 4, 16, and then we use shortening or puncturing and make a block length 14 polar code. So general case is we combine n identical and independent channels. X1, X2, Xn are their inputs. They must be independent, and each must be uniformly distributed in 0 and 1, so that each channel achieves its capacity. So the combining process, Gn matrix, which is a polar transform, this is a 1-to-1 mapping, and these inputs U1, U2 up to Un there must be some condition on these two, so that we end up in x1 up to xn being independent and uniformly distributed over 0 and 1. Okay, so this GN matrix is called in other chain, for example, this is called polar transform. This is an n by n matrix whose rows and columns are completely independent. So this is not like other codes whose number of rows and number of columns are different. Here we have n number of inputs and n number of outputs. So one-to-one mapping we have. So if we make so that u1 up to un are independent, each uniform distributed over 0 and 1, then the x1 and up to xn will also be uniform over 0 and 1 independent. Very clear because of the one-to-one mapping of gn and the properties of the input alphabet u1 up to un. So if x1 and up to xn are independent of each other, then we can write this term as a splitted form, as a splitted term like I of x1 y1 plus I of x2 y2, and each has input uniformly distributed, so each has channel IW. So this total capacity is equal to n times IW, summation of n terms and each term IW, because capacities are identical. So, and since we have one-to-one mapping, and from x we can determine y, and from x you can determine u, and from u you can determine x, so we have no problem in writing this expression. So we ended up in a combined channel whose capacity is equal to the sum of the capacities of independent identical channels. So nothing is lost. Now we have a process of splitting. We got this from the previous slide. Now if we split this using mutual information, so we have a summation inside which is there are n terms, and each term represents the capacity of a channel whose input is ui, which is binary input, uniformly distributed and independent of other ui plus 1, or you can say ui minus 1 other uis. And so we ended up in a channel. It represents actually a channel whose input is ui, which is binary, which is uniformly distributed over 0 1, independent of other inputs, and output space consists of y1 up to yn and all the previously decoded bits. So this is a channel which is also symmetric and can achieve the capacity because the input output is uniformly distributed. So we represent this channel by a wi. We call this channel wi and its capacity by iwi. So we combined n identical independent channel, each with same capacity, and we ended up in n new channels which we claim that they are polarized. So the sum of n identical channels is now equal to the sum of n polarized channels. So we got n polarized channels from n identical channels. So the question is, if n grows to infinity, or if n grows very large, what are the number of those channels among these n newly synthesized polarized channel? What is the number of perfect channel among them, and what is the number of channel which are totally useless? You can ask, what fraction of the new channels become nearly perfect? By perfect, I always mean nearly perfect, whose capacity is almost equal to 1. And what fraction of the newly formed channels are such that whose capacities are nearly 0? So these channels are nearly useless. So this is an important question. One need to answer that. Polarization theorem will help us. Let us consider this picture first. So the number of good channels are, you can say, nearly perfect channels we want to determine. So they lie here. Good channels lie here, capacity near 1. Bad channels lie here, capacity near 0. So what is the total number of channels lying here? What is the total number of channels lying here? So polarization theorem says that if we apply channel polarization, then the bit channels wi's, they polarize, their capacities polarize in the sense that when size n grows, if we have a delta which is between 0 and 1, so some of the channels lie here. Some of the channels lie here, and the fraction of these channels which lie here approaches the capacity of the original channel. Or I can rephrase it in other words to make it more clear for coding people. A good channel is used for a bit transmission. So the number of good channel means the number of information bits. So the number of information bits divided by the total code block length, which is a ratio which is equal to the rate of the code. So the rate of the code approaches the capacity of the channel. So this is like the polar code achieving the capacity. So the fraction of good channel is equal to the capacity of the original channel, and similarly reflection of the bad channels are used channels equal to approaches 1 minus capacity of the channel. But this delta can have any value between 0 and 1. We cannot want like to delta to 0.5 and good channels all distributed over here, bad channels distributed over here. We must want delta very small, so the good channels either lie nearly perfect one or nearly 0. So rate of polarization theorem, which was developed by Teletar. So it says that delta is almost equal to 2 raised to power minus square root of n. So if we make n very large, then this interval becomes very small and this interval becomes very small. So we have nearly totally we have either nearly perfect channels or nearly useless channels, and we do not have mediocre channels, or their number is very small. So the rate of polarization actually very slow for asymptotic block lengths. This proves to be a good, but for short block lengths or moderate block lengths, this delta can be a bit longer, and we can end up with mediocre channels. So polar codes, they're good for short block lengths. They can be used to show that they achieve the capacity of channel under successive cancellation decoder, but for practical blocks, they are as powerful as other codes. So let's consider encode. So let's say that we have so we know that we must have 4 good channels and 4 bad channels. So rate 1/2 can be achieved. So the first step is to, among 8, we want to identify good and bad channels. So we list down their capacities like this. So based on the capacities, we select good channels and bad channels. So those with highest capacity, we call them information channels, and we transmit data over it. The red, these are information channels, and those with lowest capacities, we call them useless channel, and we fix them to some value, and they are called frozen channels or useless channel. And in our case, we fix them to input 0, you see, and it is known both to encoder and to decoder. Then we apply data over the information channels, as you see, and apply zeros over the frozen channels only. So now now we see that there are 3 layers, or 3 stages. One stage is this one, another stage is this one, and another stage is this one. So the number of stages in a polar encoder is equal to log 2 of n. So n here is 8, so log 2 of n is 3. So we have n variables at every stage, and we have log n stages. So the complexity is n log n. N variables at every stage and log n. So the complexity is n log n. So encoding is very easy, just modulo 2 addition. We have to do it stage by stage. So fully parallel encoder works very efficiently. Encoding complexity we have explained, log n stages and n variables at every stage, so complexities of the order n log n. Then we have successive cancellation decoder. Okay, let us consider WI channel. WI channel, its input is UI. So and its output is Y1 to Yn and all the previously decoded bits. Okay. So this UI is an input to a channel WI. So we have 3 cases. Okay, for successive cancellation decoder, as I previously said, that the decoding order is important. So we have the observation space Y and all the previously decoded bits. So to decode UI, we also must know all the previously decoded bits from U1 up to UI minus 1. Okay, so if this UI was an input to a bad channel, you can say frozen channel, then we know we have frozen this to 0. So we can know it for sure. Just as we know its index, we can determine it was frozen, so we can decode it as 0. Okay, if it was input to an information channel, then we need to determine the log likelihood ratio over here from its transition, from the transition probabilities of the channel WI, like this. Since we have assumed BPSK modulation with 0 being labeled as plus, transmitted as +1 and 1 transmitted as -1. So if we have log likelihood ratio of this root node greater than 0, and we decode it as 0, otherwise we decode it as 1. So among these 3 cases, so we need to know the transition probabilities at this root node for wi, and output space is very large. If n is very large, y1 to n, u1 ui minus 1 given the ui. If for a random polar, this transition probability calculation is very tough. Root node LLR calculation is very tough. But thanks to the recursive structure of polar code, we can divide, this cumbersome task calculation, this log likelihood ratio at root node can be divided into very small manageable pieces. We will see. This is the recursive structure of successive cancellation decoder. We start with the channel observation. We calculate the log likelihood ratio over here. Very easy, involve just one space. Output space just consists of the y at that point, and we calculate log likelihood ratio. Then we propagate these log likelihood ratios at internal stages, 3 stages again in the decoding also, log n stages, n variables at each stage, and log n stages, so n log n complexity of the successive cancellation decoder as well. So these log channel LLRs are propagated through FNG's functions, 2 type of function, and so then output space increases it propagates through these layers. We started with an output space of 1 only, and then we end up here in the channel LLR, whose output space includes all the required one, which its expression must include. And then we apply the hard decision over here. So we decode it as U0, U2, U1, U2. All these we decode in a sequential manner. Successive cancellation decoder is highly sequential. Okay, so we start with channel observation. We calculate the channel LLR like this. Just involve one output variable y. So very easy to calculate this one, and this will lead us to the root LLR calculation. So at internal levels and internal stages, we have FNG's function. We start with this one. Then we at the internal levels we calculate the using FNG function. We calculate the internal LLRs at the internal stages until we reach the root node, and we calculate the root LLR at the decision node, which is like this, which we wanted to calculate. So from starting from very small manageable pieces, we ended up in a very complicated expression, but we calculated it in a very easy recursive manner. So now this this root node LLR can be used to decide about the bit being decoded. Okay, how this works? Starting with channel LLR, calculate their LLRs from observation, propagate at internal levels like this, FNG functions only, and then decide it through hard decision rule. Similarly, decode U1. We see FNG functions, how they work. Very easy recursive structure, very easy to see and beautiful to see it. It's just like a butterfly structure, fast Fourier transform structure. So it has efficient implementation algorithms. Okay, the error performance of polar code, if we want to code at the rate which is less than the capacity of the channel for a binary discrete memoryless channel, symmetric channel, the block error rate if under successive cancellation decoder is given as this, and where beta represents the error exponent, which is almost equal to 0.5. So the error exponent is not very good actually. In fact, using Shannon random coding approach, equivalent to Shannon's random coding approach, if we use a random permutation, a random polarizer, we can end up in a beta which can be strictly greater than 0.5. But the problem with the random polarizer is that lake structures and are very complex to implement. While polarizer, although it achieves an error exponent almost 0.5, so the rate of polarization is not very fast, or you can say the error rate is very not good, but not that much good. It's good, but for short block lengths, we do not achieve block error rate, which is very good. But the thing is that with this polarizer, under successive cancellation decoder, the complexity is very manageable of the order n log n. We have seen it already. This is construction of polar codes. I will not discuss in detail, but for a practical code, if we claim that it achieves the capacity, we should have 3 things. Number 1, we should be able to show that it achieves the capacity. Second thing is it should have encoding and decoding complexity very low. or you can say manageable. And the third thing is complex. Is construction should be explicit and should have low complexity. This is for a practical code. We know from the Shannon that codes exist which can achieve the capacity, but nobody was able to explicitly construct such codes with complexity and implement them in coding and decoding complexity. So polar codes have all qualify all these three criteria. Encoding and decoding is low, they can be shown to achieve the capacity, and their construction is also very manageable. If we use density evolution, we end up in order n log n, but the convolution implementation is tough, so we approximate it, and there is a tall inward method, so the implementation causes a little more complexity of the n polynomial log n. So, but still it is manageable. Many other techniques used, but each has its own disadvantages. So Gaussian approximation method also used there, which works well for the channels, but when block lengths increases, it does not work well. Now, up till now, we consider successive cancellation decoder. Successive cancellation decoder is very sufficient, in fact, to show that polar codes achieve capacity asymptotically when the block length is very large. So SCD can be used to show that polar codes achieve capacity. But what about short and moderate block lengths? When the block length is short or moderate, SCD is not powerful enough to challenge LDPC and turbo codes. So we cannot use for practical purposes a successive cancellation decoder. Then we switch to SCD with list decoder. SCD list decoder is it uses SCD, but like LCD, which is a depth first search algorithm, it searches only one path. It only one possible path with the highest likelihood, with the most likely word or most likely path. Unlike that, list decoder starts with SCD, and it searches many possible paths. And if the number of paths increases beyond some limit size L, so we only select the most likely search path and say the most likely words from the list. So this ends up in a good result for performance. But the complexity is a little more, but still algorithm exists, and these decoders are implemented in hardware, both in software, and are available. Okay, so here is the performance. We started with SCD. Red shows L1, which shows the list size is 1, which is SCD. If we increase the list size to 2, the performance improvement is satisfactory, in fact more than satisfactory, with list size 2. If we, in this block length is 2048, rate is half, and this is for IWGN channel, AWGN channel. If we increase the block length, performance improves. The green line shows the list size 8 for the pink line, performance is improving. The list size 16, performance is improving. List size 32, performance is improved. But beyond that, improvement in the performance is not that much. And here we see that at high SNR, it is settling to some floor. But an error flow, actually, it is the ML bound performance of the polar codes. The ML bound, where you can call it the list performance of successive cancellation decoder, with the maximum possible list size. So definitely one cannot exceed with whatever the list size may be. Beyond the ML bound we cannot go. So the maximum achievable performance that we can obtain with the list decoder. So even with ML decoding, polar successive cancellation decoder is not strong enough to challenge the state-of-the-art codes like YMX turbo codes and YMX LTPC codes. Blue line and pink line shows YMX turbo and LTPC codes. This one shows the ML performance. You can say the best list size performance of list decoder under SCD. So still we are way behind these state-of-the-art performances. So we need to do something. So we end up in a list with they are designed based on improving or increasing the minimum distance of the code, the code words minimum distance. We are not up to it. So in some way by including, let's say, CRC, then its performance can be improved a lot. Here we see that we CRC16 added to list 32. The green line shows its performance, which is better than the YMX Turbo and YMX LDPC code. So we have achieved state-of-the-art performance, and this is the code list decoder with CRC, which will be used in 5G. So very efficient code, very efficient performance, efficient implementation, and these are the codes of the future actually. Still, we can go beyond this. Just recently in 2019, Arikan again introduced another code, polarization adjusted convolutional code. So we can reach limits actually for finite block actually. So these PSE codes performance is remarkably close to finite length capacity. So this red line shows the best possible performance of any code or any random code that can be achieved for a given block length, for a given finite block length. We cannot go beyond that no matter what type of code we apply. The best code, any code, even theoretically speaking, which cannot be implemented, but no code can go beyond this for finite block lengths, not asymptotically finite block lengths. But we see that this PSE code just with a block length of 128 can reach this performance. We call this dispersion bound, which is the best performance that can be achieved by LGN channel approximation using polyandry. So PSE use this. This is a major breakthrough in coding theory, and still research is being carried out in this field, and they are very new, and a lot of open areas exist in these codes, construction and decoding. Okay, how these works actually, just to give you a main idea. When we were designing polar code, we decided some good channels and some bad channels, but we know that for finite block lengths, polarization is not perfect. We do not end up in perfect channel and useless channel. We end up in relatively good channels and relatively bad channels, but we freeze the bad channels to some fixed, so we do not use them, and we use the good channels, although their capacities are not 1. So while in doing so, we discard in some way, you can say. So we discard their capacities. But we discard these capacities, so we cannot achieve the capacity of polar codes under successive cancellation decoder with finite block lengths because of discarding these capacities. So PSE makes sure that we do not discard these channels and we do not discard these capacities, but we use these capacities also in some sense. So in this way, it achieves the capacity even for finite block length. So this is how it works. This is its workflow. This is not actually the polar code is not actually working as an inner decoder like we have concatenated code decoders, because okay, so this is rate profiling. Rate profiling is just like the selection of good channels and bad channels before convolutional decoder, which is a pre-coding step. And here we have dimensions of V and U the same, but we have some zeros due to fixed useless channels. And here we have dimension of U and X the same. So this is a one-to-one mapping. You can call this a mapper actually. This is not an encoding process here, like not in a concatenated code we have inner code. So this is not like this, is a one-to-one mapper. Then we have channel. Then we have an SCD over here which calculates the soft matrix, which pass but do not decide do not hard decode the bit. Instead it passes to a sequential decoder, which is a search path algorithm, which uses search path algorithm, and based on these matrices, among many possible paths, it searches the best path. It can go to and fro. Arikan suggested Fano decoder over here. So how it works, and this is still a new area, and there is a lot of work being conducting these days in these codes. So a lot of potential areas. This is the summary. PSE code can present block length n, and this is the rate profiler KB rate shows, and rate profiler indices of good channels and bad channels. C is the impulse response of the convolutional code. So this is how it works. And then I must acknowledge the contribution Okay, so before that, let's future work. Future work. A lot of areas open in polar course. Okay, so this is. Uh, I must acknowledge the contribution of Erdal Arikan, Professor Erdal Arikan Hoja, um, because some of his materials I used with his permission. So his contribution is highly uh, appreciated, and thanks to him. And thanks to you for listening, and thank you.